This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So just a short announcement. We will cancel today's tutorial lecture because we didn't cover enough material on frequency domain methods. So 2 p.m. today, 2:15, please don't turn up for the tutorial. We will do that next time because that tutorial was supposed to be all about Bode and Nyquist. Because we repeated midterm, we didn't cover enough material. So, all right. So today's lecture is starting a completely new sort of set of analysis and design tools, which are generally called frequency domain methods. So the fundamental concept that we will use in all these analysis and design tools is the concept of frequency response of a linear time invariant system. So this lecture is an introductory lecture for frequency response. And we will introduce it and we will explain how to compute it and how to graphically represent it using so-called Nyquist plots. So that's the purpose of today's lecture. So I'll first motivate things a bit. Then I will introduce frequency response, and then I will talk about how to mathematically calculate it and graphically represent it. So, and then we will summarize. All right, so these methods, frequency domain methods, are really instrumental in analysis and design for control systems, and I would say they are probably the most powerful set of methods that you will learn in this subject. So, why we start with root locus and all these other designs, PID control, they are perhaps easier to introduce concepts of design. But the most powerful design methods that you will learn are actually frequency domain. Frequency domain methods are also interesting because you can experimentally determine frequency response of a given system. So you can perform a set of experiments and plot the frequency response using techniques that we will present today. For the rest of the subject, we will talk about so-called Nyquist plots and Bode plots, and they are just two different ways of representing the same thing. There are two different ways of representing frequency response, which we introduced today. So all of these tools are all related, and they all go under the name of frequency domain tools. All right. You will see later on when we start talking about frequency domain compensation, you can really design very cool controllers using these tools that satisfy performance and robustness specifications which you cannot pose in time domain. It's hard to deal with those specifications in time domain. So you would really genuinely get a new set of tools which is very powerful, all right? And we will learn how to use them for both analysis and design. So just to sort of put things in context, in the first part of the subject, first half of the subject, we were talking about, differential equations. We were talking about transfer functions. So we basically concentrated on the first two of these sort of sets of tools, right? And for the rest of the subject, we will talk about frequency domain methods. So you can think about signals represented using their Fourier transforms and system represented with its frequency response. Roughly speaking, I mean, I'm just sort of trying to put things into context. So we will talk today about how to define and how to determine frequency response of a stable linear time invariant system as an introduction to all of this sort of area. All right, so let's first define what we mean by frequency response. So, by the way, you've probably covered, electrical circuits or, some classes of linear systems, like in mechanical systems. If I have a stable system, right, like an electrical circuit, and then I apply a time-varying voltage to the circuit that oscillates at a certain frequency, then what would happen to all currents and voltages in the circuit? After the transients have died out, what would happen to them? Can we say something about frequency of all signals in the steady state? They are the same. So stable linear time invariant systems, when you hit them with a time-varying input of a fixed frequency, so let's say 50 hertz, right? Then after transients have died out, all signals in this stable system would start oscillating at the same frequency. Now amplitudes and phases may be different for each different current and voltage in the system, but the frequency will be the same in steady state. So that actually fact would lead to the definition of frequency response. So what we are dealing here with is we have a causal, stable, linear time invariant system. So the system is now stable. There's no instability here, right? So, and we are saying, let's hit the system with an input which has certain amplitude, AU, and it oscillates at a frequency omega. So it's a sinusoidal or cosine, input. And what we are saying is that after transients have died out, then the output would oscillate at some different amplitude, AY, and there will be the same frequency omega, right? Omega is the frequency of the oscillation of the input. Omega and the input and output are the same. And there will be some phase shift, this theta phase shift. So this fact is a property of stable linear time invariant systems, causal stable linear time invariant systems. So note that what I'm using here is a steady state response. So transients have died out, and I'm just looking at what happens to the output in steady state. So this fact is really fundamental to linear systems. If you have a nonlinear system, then what can happen is that the output in steady state may be chaotic signal. It's not even a periodic signal. It may happen that the output has a frequency that is a multiple of the input frequency. It can be like higher or lower frequency. In nonlinear systems, you can have, output in steady state being, contain multiple frequencies. So this sort of property that in steady state you get a sinusoidal output at the same frequency, maybe different amplitude, different shift, that's a property of linear systems, right? And nonlinear systems typically don't have this property. Now, what we would call gain in this, so by the way, it's really useful to represent everything graphically. So if we represent with green the output of the system and by blue the input of the system, then typically you will have something like this, all right? The input oscillates like this, and then when you plot the output, it will oscillate at the same frequency, so the period of oscillations in steady state will be the same as the period of oscillations of the input. But then the amplitude of the green signal will be different in general from the amplitude of the blue. And also there will be this shift, which is captured by this delta t. So shift in the period, right? So from this delta t, we can define, the phase and phase would be this theta in the equation above, right? And we will have the gain. So what is the gain at that frequency? Well, it's the ratio of the input and output, output and input amplitudes. So what does this mean? Well, the gain basically tells you by how much the system would amplify the amplitude, right? And the phase will tell you how much are these two signals shifted with respect to one another, right? Now note that both gain and phase would depend on frequency omega. So for each different omega, I will have different gain and different phase, right? Now these objects, gain and phase, will be used to define the so-called frequency response of the system. So what would be frequency response? It would be basically a graphical or mathematical representation of what gain and phase, how they change as a function of omega, right? So if you know how both gain and phase change from omega 0 to omega infinity, that's basically frequency response. That's what we will call frequency response, right? So are there any questions just about this part? No? By the way, one important thing is that you can determine this gain and phase for any given frequency experimentally. So how would that work? You apply a sinusoid of a certain frequency, you know, at the input, and then you wait until the transients have died out, and then you record what the steady state is. And then from the steady state output and the input, you can calculate what is gain at that frequency omega and what is the phase at that frequency omega. So you can experimentally figure out all of these things. You get an experiment, you record what YSS is, you know what U is, and then you can calculate from these diagrams, right? You plot these guys, and you can determine what gain and phase are. Now, if you do frequency sweep, so you start from omega small, quite close to 0, then omega 0.1, 0.5, you can have a frequency sweep, and you can get this gain and phase for each different frequency. That would give you an experimental sort of measure or sort of experimentally determined frequency response of the system. Now you may wonder, why do we bother doing this? Well, this is a foundation for a range of different analysis and design tools, which we will learn, right? So note, steady state output is given by this, and we will distinguish the two cases. When theta is positive, we will talk about lead system or network. So, and when theta is negative, we will talk about lag. So the steady state output is lagging, you know, the input, or leading the input. So that's just terminology that we will use, all right? And that has to do with whether theta is positive or negative. What is theta? It is that sort of shift in phase that we get with respect to between input and output in steady state. All right, so what is the objective of this lecture, or objectives? Well, we want to first rigorously prove what I just said. I said that if I apply a sinusoidal input to the system, stable linear time invariant system, then after transients, I do get a steady state output which oscillates at the same frequency. Maybe different amplitude, different phase, but the same frequency. So we will prove that fact. We will also learn how to rigorously calculate phase shift and the gain from the transfer function. So if I give you the transfer function, I will teach you how to obtain the frequency response mathematical description of the gain and phase, right, in the frequency response. We will introduce this notion of frequency response of the system and learn how to calculate it, and also provide graphical representation of frequency response. You will see that the gain and phase, as defined here, can be used as like polar coordinates in plotting the frequency response. So this will lead to naturally to the notions of Nyquist plots and Bode plots for linear feedback systems. And they are underlying a lot of analysis and design techniques we will learn. You will see that you will be able to determine stability from frequency response, and you will be able to design robust controllers that tick off some performance specifications in terms of response, damping, overshoot rise time, but also robustness to disturbances in certain frequency bands. Internal model principle, allowed us to perhaps track or reject disturbances at a single frequency. If you use these methods, you will be able to deal with disturbances in range of frequencies, which internal model principle can't deal with, right? So you can have like infinitely many frequencies that you're dealing with, and you're designing a controller that ticks off a box in terms of performance for the range of frequencies, both for tracking and for disturbance rejection. So it's a very powerful set of tools. All right, so when we talked about time domain specifications, we were using special input. We were using step input as a test input to our system. And that's how we defined overshoot rise time, settling time, right, and steady state errors, right? So sometimes we use ramp inputs, sometimes step inputs, etc. In all the frequency domain, analysis design tools, we will be using sinusoidal inputs, right? It's almost like, think about Fourier series, versus, Taylor series, right? So now we are talking about Fourier series style sort of questions. Now, in order to prove the first fact, which is basically steady state periodic response, we want to use a test input. In this case, let's use the test input equal to this. By the way, this input, it's Ej omega t, can be represented as a sum of cosine and then j sine omega t, right? Using the Euler formula. By the way, don't be alarmed that I'm using here a complex sort of input, because this j, I can't really implement this, in reality. But what I can do if I add, this to another e2 minus j omega divided by 2, I just get cosine omega t. So actually, and because of linearity, I know that response of these two inputs, would be sum of responses of the inputs to corresponding guys. So if I do one of these guys, I'm mathematically, I can easily go to the real inputs, right, where I don't have j at all. So this is just going to simplify calculations, because the Laplace transform of this input is actually equal to this. If I wanted to have real input, like sinusoidal, what's the Laplace transform of the sinusoid? You will have s squared plus something, right? Plus omega squared. Well, this is simpler to use, right? Rather than using squares, I've just used this guy, right? But it's easy to go all the way to use real inputs. So what I'm now assuming is that I have a causal, stable, rational transfer function with non-repeated poles. Why non-repeated poles? Well, calculations are simpler. We can repeat this proof for repeated poles, but then calculations will be just a bit more difficult, and without loss of generality, I can just concentrate on this. So all the main ideas will be still captured by what I'm going to do next. So I will restrict the class of plants to have non-repeated poles. The system is stable, causal, stable transfer function. All right, so what I want to do now, I want to calculate response of this system to this input. So I have this input, and I want to calculate response of this system. So we are calculating sinusoidal response. So how do we do that? Well, it's really quite simple application of partial fraction expansions. So what I'm doing is the output of the system to this input, would be basically equal to this g tilde, where I multiply the transfer function. By the way, the transfer function that has non-repeated poles. All poles are different, so all the alpha k's there are different. And this last term here is exactly the Laplace transform of the input. So the output of the system is product of the transfer function times the Laplace transform of the input. So I can rewrite everything in this way. Know that I here now have an extra pole. I subsumed this guy here as just like an extra sort of pole in this G tilde transfer function. So since all the poles are now, non-repeated, I'm now doing partial fractional expansion. So what's partial fractional expansion in this case? Well, it's equal to this. Because I have non-repeated poles, that's exactly what it is, right? So what are the residues? Well, residues are calculated using formulas I gave you earlier. So this is the formula for calculating residues, right? Corresponding to each alpha k, there corresponds residue b tilde k, and this is the formula that we use. So B1 is equal to this, so if you do all the calculation, that's what you get. So in the end, all the B tildes up to n are given by these formulas. Why? Well, because when we plug in your G tilde into the equation for calculation of residues, you would actually get these guys. Now I'm avoiding using the J omega. You know that J omega is now considered as one of the poles in this G tilde transfer function. I will calculate its residue at the end. But all the residues due to the poles of the transfer function, original G transfer function, are given by these formulas. So what is the B tilde n plus 1? Well, that takes a bit more sort of care. So now I have to plug in the formula for residue for this case, but now this S minus J omega and S minus J omega would cancel because I'm looking for residue with respect to J omega pole that is due to the input. Those two things cancel, and what I end up with is just G evaluated at J omega. And what is G? G is the original transfer function, so G is the transfer function of your plant, right? So the overall output, if I take the inverse Laplace transform now, so by the way, I have now partial fractional expansion. I've calculated all the B tildes. I calculated all B tildes, and how do I find the time response? I take inverse Laplace transform. So inverse Laplace transform is basically the sum of inverse Laplace transforms of all the guys due to the poles of the plant, plus this guy which is due to the last input, right, term. Now note what is interesting here is because we assumed stable plant, all alpha k's will have strictly negative real parts because we have stability of the transfer function of the plant. So all of these guys would converge to 0 as time goes to infinity because alpha k's have strictly negative real parts. The plant is stable. So all of these exponential terms would converge to 0. But this guy here would continue oscillating because you have this Gj omega is just sort of a constant evaluated, it's a constant number, right? But then you have this e to j omega t. Well, what is that? Well, that's exactly something that looks, like this, right? Ej omega t is this signal here. So you have persistent oscillation, right? So what is this telling you? Well, this guy would decay to 0, and what remains in steady state is just this guy. So it is this guy that determines the frequency response, or it is actually G of j omega completely determines the frequency response. Yeah. So by the way, you can get step response from all these calculations when omega is equal to 0, because step response is like frequency of that signal is just 0. It doesn't oscillate, right? So that's an interesting thing. So by the way, transients, all this part contributes to overshoot, undershoot, all of these things that we talked about, rise time, settling time. But steady state, is determined in this case just by the frequency of the input signal omega and the transfer function. You see, G is the transfer function, and then omega is the frequency of the input signal. So if you know the frequency of the input signal and you know your transfer function, that completely tells you what happens in steady state when you apply sinusoidal inputs to the system, right? Here is what it looks in an example. So if you look at this example where transfer function is 4 over 2s plus 1, and you look at the input signal u of t is sine 5t, which corresponds, it's equivalent to Laplace transform of 5 over s squared plus 25. when you find the output of this system to this sinusoidal input, you can see that it consists of two parts. You know, it consists of the transient part, and it consists of this steady state part. Now note that what I did is I rewrote the steady state part as the magnitude of this G evaluated at J5. Why I chose J5? Well, that's exact, 5 is the frequency of the input signal, right? And then I wrote the rest is sine 5t. 5 is still the frequency of the input signal. So the output frequency in steady state will be still 5, the same as input frequency. And then I had this phase shift. By phase shift, I wrote there is the phase of G evaluated at J5. Why J5? Note that here we have G of J omega determines the steady state. So if you specify omega, in this case 5, then you have to substitute instead of omega 5. If this was omega equal to 10, you will substitute 10. So I can rewrite this whole term as sort of magnitude, you know, times sinusoid, you know, oscillating at the same frequency plus phase shift. So I rewrote this guy here just in this way, right? So what does this tell you? Well, it tells you that if you know the transfer function, you can quickly determine what the response of the system is to steady state in steady state to a sinusoidal input at a fixed frequency. So what you need to do is, if the frequency is 10, you evaluate transfer function at J times 10, find the magnitude of that object now. It's basically transfer function evaluated at a specific complex number. You can find its magnitude and phase. And these guys are exactly giving you the gain and the phase in steady state response. So what is this norm of G at J5? I will go back here. That will give you exactly this guy. Right? And what is the phase of G at J5 is exactly this guy. So we learned now how to calculate mathematically. If I give you a transfer function, and if I ask you what is the gain of the system at that frequency and what is the phase at that frequency, you can mathematically calculate them from the transfer function and the frequency of the input signal. Yeah. So using these formulas. So what would responses of the system what the response of the system looks like? Blue thing is your like input, and the red thing would be sort of the output. So note that the output sort of starts, sort of moves for a while, right? And then settles at some. So from this point onwards, it looks like just a sinusoid. There's no movement anymore of the sort of average around which it oscillates. It just sort of settles, average settles at 0, and from that point onwards the transients have died out, and that's the steady state. So in steady state, the red signal looks like just a sinusoid, but it's different amplitude and is shifted. We can calculate this amount of amplitude, you know, and shift from the transfer function and the frequency of the input signal, just by using these formulas there. All right. Are there any questions? All right. So, in steady state output can be represented in this way. We obtain this from partial fraction expansion, right? We said the first part, transient part, dies to 0, and this is the only thing that remains. But we can rewrite this in this way, in polar coordinates, where this is your magnitude, basically, and the rest includes the phase. Omega t, omega is the frequency of the input signal, right? So how do I calculate now the gain and phase? Well, you tell me which frequency of input you have. I plug it into the transfer function G. I plug in J times the omega of the input signal, which may omega equals 10, for instance. So you substitute J10. You find the magnitude of that complex number, right? That gives you this guy, right? And how do I get phase? Well, again, we have formulas for phase, right, of a complex number. So G evaluated J omega is just a complex number, right? So you need to represent this complex number using phase and gain, and you immediately get the gain of the system and the phase of the system at that frequency. So as we said, so steady state output is periodic of the same frequency omega, but scaled in magnitude by this and shifted in phase by this. Right? So, and these are the formulas now for calculating that gain and phase. Right? So note what this tells you. So it's interesting, you know, just think about a mechanical system. If I have so this pole has a mass, right? Certain mass, right? If it's heavy, right, the dynamics will be different from when it's light, right? So if I apply periodic force to this and I shake it, if I want to shake it with a certain frequency and force of the same amplitude, then, you know, if it's a light thing, the amplitude would be larger, right? If the frequency of the input is low. So if the frequency is low, you know, the amplitude of oscillation, which is the output, would be high. If I try to shake it very fast with a different frequency but the same amplitude of input, the amplitude of oscillation of the output would be smaller. I just can't, you know, if I want to shake it very fast, you know, and that tells you that at different frequencies, the amplitude of the output would change and phase would change as well, right? So this gives you a bit of sort of intuition of why, you know, and obviously if I now took like 10 kilos, you know, I have a gym, you know, at home, so in my home, so I have lots of weights. If I want to use a 10 kilo dumbbell, right, to shake, there's no way I will be able to shake it so fast, right? So the amplitude with the same force, right, high frequency, will be very low. I would just I can't move it, right? Because I want to shake it, you know, both ways, right? So obviously the model of the system, the transfer function, in this case mass, determines the transfer function, and the transfer function determines then what would be the output amplitude and what would be the output phase, right? This is a property, I emphasize, this is a property of linear time invariant stable systems. If you have a nonlinear system, forget about frequency domain analysis. Generalizations to nonlinear systems are very limited. They are not general. So this is a very powerful method for linear systems. If you have some nonlinearity, forget about it. What's also important actually is that if the system is infinite dimensional, meaning that it's described by partial differential equations, but it's linear, frequency domain methods still apply. So that's a power of frequency domain methods as opposed to, you know, Laplace domain that we did before. This is a very powerful set of methods. You can deal with time delay systems. You can deal with infinite dimensional systems. So for instance, Navier-Stokes equations linearized, or Maxwell equations linearized. All of these are nonlinear in general. But if you linearize these guys, you will be able to use frequency domain methods. Very powerful. We will sometimes talk about time delays and frequency domain of time delay systems. That's an infinite dimensional system, right? But you know, we won't go into, you know, these partial differential equations. It requires still more sort of more mathematical tools. All right. All right. So, what is an important link? Well, if you think about a Fourier transform, so suppose now I have an arbitrary signal and I find its Fourier transform. Think about Fourier transform. First, think about an input signal which is a finite sum of finitely many frequencies. Well, because of linearity, I can find steady state of this system response to each of the individual inputs, and then I can sum up these individual components because of linearity to find a steady state due to that sum of the sinusoids. So if you have similarly, if you have a Fourier transform of a signal, it's like infinitely many frequencies, but because of linearity, I can just add contributions of each of these. So this gives you a very sort of nice sort of interpretation of what's happening in linear case because steady state response due to a signal that is a sum of sinusoids is the sum of steady state responses to each individual sinusoid, right? So, and this is because of linearity. So we would use superposition principle to actually conclude something like this. All right. Now, the next slides will introduce a graphical representation of frequency response. So by the way, if you think about this object, so the frequency response is this G, J omega. So if obviously the frequency is omega that we are interested in, like in experiments, would be just positive, omega from 0 to plus infinity. But mathematically, we would often want to plot what this G of J omega does, even for negative frequencies. Mathematically, it would turn out to be a very useful mathematical object. It would be easier to work sometimes with that mathematical object. So actually, what we will be plotting here is G, when J omega sort of changes, so omega changes from minus infinity to plus infinity. Interestingly, because G is a transfer function which is rational, let's say we are working with rational functions with real coefficients, then this, there will be some sort of properties of this G, J omega, where G at J omega for omega 0 to plus infinity would be a mirror image of G at frequencies minus infinity to 0. So you can plot just G for positive frequencies, but plotting it for negative frequencies would be just sort of a mirror image. We'll talk about that in a moment. So what is sometimes useful to represent this G of J omega graphically. So obviously G for any omega, G J omega is a complex number, right? I evaluate a transfer function at J omega, so I get a complex number. But imagine now I'm varying omega, and this G of J omega changes. So it's a very cool thing to plot how real part of G J omega and imaginary part of G J omega change as a function of omega, as omega changes from 0 to infinity. That's basically giving you opportunity to graphically represent this object here, this frequency response. So we want to now do that. What is really cool is that there are very nice interpretations of the gain and phase. So suppose that you basically consider this G, J omega, and then you consider, let's say, frequency omega 3. When you have frequency omega 3, you evaluate J omega 3 into the transfer function, and that would be a complex number, which will have a real part and imaginary part, right? But you know, if you if you now change omega 2, you will have a different complex number. So G J omega 2 is a different complex number. G J omega 3 is a different complex number. So you can then plot how this G J omega changes as we swipe frequency from 0 to infinity. Now what's a cool thing is that if we look at polar coordinates representation, for instance, for omega 3, we look at polar coordinates of this point, right? This is on the frequency response. Well, the distance from the origin turns out to be basically the magnitude of G evaluated J omega, and this angle here turns out to be the phase, exactly. Right, so this phase of G J omega and magnitude are really polar coordinates of this plot. So for each different omega, we get a different point on the plot as omega changes from 0 to infinity. That is a graphical representation of frequency response, right? Okay. I mean, you must have seen body diagrams before. So this is just an introduction. We are going to arrive at body diagrams soon. So know that this curve here can be obtained from experiments. What you can do is you can run an experiment, apply sinusoidal input at some frequency, like frequency 1. You wait for steady state for steady state response, transients die out, and then you record the output amplitude and phase, and then you calculate from those, like input amplitude and output amplitude, you calculate what is the phase and magnitude of the system frequency response at that frequency. So you get 1 point on this plot. So each of these omegas, or each of these points here would correspond to one such experiment. So then what you can do is so-called frequency sweep. So you just repeat this experiment for different frequencies, and you get lots of points, right, in this plane, and then you connect them. That's how you would experimentally determine frequency response, right? So it is possible to do it experimentally. All right. Now, because this is so important, we will use it over and over again. It's useful to see some examples of frequency responses for some transfer functions, because you would need to be using this very sort of fluently. Right? So it's important to see some examples, and the rest of the lecture is really looking at different examples. I won't go through all of them. You have all the calculations, and you can check that you indeed get. I'm more interested to show you graphs and explain just at a high level, but mathematics you can find in Ogata's textbook. This is all taken from Ogata's textbook. All right, so let's look at one example. So suppose that you have this G of S. So so how do I get G at J omega? I replace S by J omega. That's how I get G of J omega, right? So I get my transfer function that is a function of S, and I substitute instead of S J omega. That's my frequency response. And then you can look at, what is the magnitude of the guy and what is the phase of that guy, as we sort of defined them earlier, right? Well, for positive frequencies, right? So by the way, if you set omega equal to 0, look at this GJ omega on top. So the first line. So when I set omega equal to 0, what do I get? What is G at 0, or J times 0? 1. So what is the point on this diagram that corresponds to that frequency? It's this guy here, right? Because it's 1, so this is a complex plane, right? So there's a real part of J omega, and imaginary part. So real part is 1, imaginary part is 0. So this point here exactly corresponds to omega equals 0. As you go around, right? So by the way, as omega goes to plus infinity, what would be J at infinity from that formula on top? 0. So what is that point? Well, that point would correspond to this guy here. But there are all the intermediate points you can calculate using those formulas. So by the way, this is plotted only for positive frequencies, and I told you that for negative frequencies we can just mirror image it with respect to real axis. So you will get that this is a complete frequency response plot. So as omega goes to minus infinity from this side just above, then omega would increase this way. For omega 0, this is the point, and then for omega plus infinity, it's this point back. So that is the frequency response for all frequencies. For a simple linear system with a single stable real pole, right? One example, by the way, G at 0, this point here is related to steady state errors of GS in open loop transfer function. If G was the open loop transfer function, if you remember how we were calculating steady state errors, then we did have complementary sensitivity evaluated at 0, or we could actually relate it to open loop transfer function at 0. So you can see that we can relate some of the things we were doing before, like steady state errors, to some properties of the frequency response. We just need to know how to relate, connect things, right? Very important, frequency response is always symmetric with respect to the real axis. That's why you would always plot things from 0 to infinity, and then just mirror image it for minus infinity to 0, right? So it's easy. How about this guy? By the way, this is a non-causal transfer function. It's like a PD controller, proportional differential controller. It's non-causal, it's not physically realizable. We can still mathematically define frequency response, using the formulas I gave you. So we are just now plotting frequency response as I defined it earlier. So this is what you get, right? So when omega is 0, what is gj omega? It's 1. But then this is that point. But note, as omega goes to infinity, then j omega always has real part 1. Real part is independent of omega. Real part always stays the same. And omega going to infinity means imaginary part blows up to infinity. So that's exactly this graph here, right? By the way, this is now plotted only for positive omegas. Negative omegas, you just mirror image. So minus infinity would be going this way, and then 0 again would be here, right, at this point. So just mirror image the thing. All right. And by the way, these are the precise formulas for the magnitude and for the phase. Well, the magnitude is real part squared, which is 1, plus imaginary part squared, and then square root of that. That's the magnitude by definition. Magnitude of a complex number is that. And this is then the phase. Think of polar coordinates. That's what we are plotting here, right? Here is a bit more complicated example where we have a second order system with some damping zeta and natural frequency omega n. So if I normalize everything so that, I'm plotting this actually object here, right? Then the zeta or the damping factor would affect frequency responses in this way. So smaller zeta would mean that this frequency response would go further away. It would make like a larger sort of, the magnitude will have larger values. Now, why is this how can we relate this fact to the resonance, to resonance sort of phenomenon? In mechanical systems or in electrical systems, there is a thing called resonance. What does that mean? When you hit the system with an input of certain frequency, then the output magnitude is amplified a lot. Well, if you have low damping, we saw that overshoots would go crazy, right? Low damping, you have larger overshoots, right? But how do we see what's happening in the frequency domain responses? Well, as these guys become larger and larger, what does that mean? Well, note, magnitude is basically the distance from, let's say, this point here to the origin. So obviously the magnitude, the amplification factor that the system imposes on the steady state response is larger and larger as this magnitude is larger and larger. So basically, what does that mean? You can have, let's say, chandelier in a church or something. There is a gust of wind, but it's periodic. Very little force, very small force, but that can cause very, very big oscillations when the input frequency is very close to the natural frequency, right? So depending on your system, so if you like to tease your friends, you can find their natural frequency so that the response is crazy, right? So you just sort of fool around with them, and then there's a screw. You say something little, right, small thing, but they explode, right? So this is like, applying small signal, but the gain in the system at that frequency is huge. My daughter is a feminist. I have to be careful how I talk to her because that frequency is very the gain is huge, right? She's very sensitive just about how I phrase my sentences around certain, issues. So that's one example, right? So what is this resonance peak? That is basically the largest distance from the origin in this plot, right? When you find the point of largest distance, well, what is this resonant peak? Well, if I pick my frequency of the input, sinusoidal input at this omega r, then the system would amplify the amplitude most at that frequency. Maybe you heard, by the way, if you go on YouTube, there are examples of earthquakes or wind gusts destroying bridges. Just go on YouTube, you see bridge sort of moving, it just sort of collapses. So what you are doing there, you are applying force at a certain frequency, and if you hit the natural frequency of the system, that peak frequency here, that might create huge amplitudes, right, in movement, and it just destroys the thing, right? So this sort of analysis is important in civil engineering, in electrical circuits, in mechanical robots, just anywhere, right? So it's a very, very important sort of set of observations. All right. One important thing, and this is one of the last things I want to talk about, is if I have a time delay, so know that this transfer function here is a transfer function with a single pole, but now I have a time delay. This exponential to minus st is due to time delay in the system. Minus SL. L is the delay. So this is basically the same transfer function as the first guy. So no, this was the original transfer function. And now I'm saying if I add a little bit of delay, so L is small, what happens to this guy? Right? So that's what we are plotting next. So what will happen, and you can show that in Ogata, there's all the sort of calculations. The frequency response would start circling around the origin. Note, this is like a spiral, and it keeps going on. It's like a spiral. There are infinitely many, sort of loops around the origin. But what's different between this frequency response and the original one? This frequency response intersects negative real axis in this diagram, whereas the original response here does not go to the right half plane of this plane, right? So introducing even a little bit of delay would mean that this frequency response will actually do this. It will go this way, and it will start circling around. This has major repercussions for stability analysis. When we start looking at Nyquist plot, you will see that this might destabilize the system or make system more prone to becoming unstable, right? So but here at this stage we're just sort of making an observation. Now look, if you go to Ogata, I love Ogata's book because it catalogs all disparate examples. So it's very useful for you to look at all these sort of transfer functions and frequency responses. So this is like a dictionary of the most basic transfer functions and their frequency responses. It will help you gain intuition. If I give you some of these things in the exam, you can say, this is it, this is that case. Obviously, I can also give you things that look much more different than this, because this is just giving you some simplest transfer functions and their frequency responses. Right? All right, so what to take from this lecture? The steady state response of a stable causal linear time invariant system would be a sinusoidal signal at the same frequency as the input frequency, different amplitude, different phase, right? So we then could introduce this frequency response. So actually frequency response is a different way to model the system. We started off modeling systems with differential equations, right? From first principles we got models, the Newton's laws of motion, things like that. We get differential equation. Then we learned by Laplace transform how to obtain transfer function. But now frequency response is just a different way to write a model. So that contains all the information about your system, everything about your system, right? And we will then, in the rest of the subject, talk about Nyquist plots and Bode plots, which would be really cool analysis and design tools. And we will use them a lot for the rest of the subject. All right, any questions? Thank you very much. I'll see you next week. So there is no tutorial lecture this afternoon. Yep.
Thank you.